somewhere in the vast and silent dark, far beyond the reach of any spacecraft or satellite, a star reaches the end of its life. Not quietly, not gradually, but in a final moment of collapse so violent that it outshines an entire galaxy. This is the origin of a gamma-ray burst, one of the most powerful and mysterious events known to science. For a brief instant, these bursts release more energy than our sun will emit in its entire 10 billion year life. And they do so in seconds. Gamma-ray bursts, or GRBs, are not common. In fact, they are among the rarest and most fleeting phenomena in the cosmos. Yet, despite their scarcity, they carry a terrifying potential. If one were to occur within a few dozen light years of Earth, and if its jet happened to be pointed directly at us, the consequences could be catastrophic. Our planet's upper atmosphere would absorb the intense gamma radiation, triggering chemical reactions that could strip away the ozone layer, the shield that protects all life from the sun's ultraviolet rays. In the aftermath, the surface of Earth could be scorched by unfiltered radiation, igniting mass extinctions, all without warning and all in the blink of an eye. These are not fictional threats. Gamma-ray bursts are real. They were first detected by accident during the Cold War in the 1960s, when satellites designed to monitor nuclear weapons picked up mysterious bursts of high-energy radiation from space. At first, their origins were unknown. Were they nearby, galactic, man-made? It wasn't until the late 1990s that better instruments and X-ray monitors revealed the truth. GRBs originate far beyond our own galaxy, millions or even billions of light years away. Their power, therefore, had to be almost unimaginable. How could something so distant shine so brightly? The answer lies in the death of massive stars. When a star, more than 10 times the mass of our sun, exhausts its nuclear fuel, its core collapses under the force of gravity. In some cases, this collapse forms a black hole. As material folds inward, a spinning disk of matter forms around the new black hole's event horizon. From the poles of this disk, twin jets of plasma erupt at nearly the speed of light. These are the gamma-ray bursts that flash across the universe. They are narrow, focused, and brief, but devastating. And they move at the speed of light. There is no warning. By the time our telescopes detect a gamma-ray burst, it has already happened. If one were close enough to affect us, it would be over before we even knew it began. Thankfully, most GRBs point elsewhere. Their narrow beams make them difficult to observe, and the odds of one aligning precisely with Earth are exceedingly low. Scientists estimate the chance of a life-extinguishing burst hitting our planet is less than 1 in a trillion over the course of Earth's history. Yet, the risk, however remote, is not zero. And that fact alone offers a strange and sobering perspective. What does it mean to live in a universe where such forces exist, unnoticed until they strike? How do we measure our place in a cosmos capable of such sudden, silent destruction? We go about our days under blue skies and quiet stars, never knowing what ancient light might be traveling toward us from the far reaches of space. But perhaps the more profound question is not whether we might be destroyed by distant energy, but how we have survived at all. In a universe filled with gamma-ray bursts, supernovae, and black holes, Earth remains a rare sanctuary of life. Balanced, resilient, and shielded by a fragile atmosphere, it orbits its star in a quiet corner of a galaxy that has seen countless cycles of creation and ruin. Somehow, against all odds, we are here. This resilience becomes all the more astonishing when we consider the conditions required for it. For life to flourish here, countless variables had to align with extraordinary precision. The Earth's distance from the Sun, the presence of liquid water, the stability of its orbit, the shielding effect of its magnetic field, and the specific composition of its atmosphere. All these factors form a narrow window of habitability. A window that could have easily closed if a gamma-ray burst had targeted our planet just once in its long past. Gamma-ray bursts also pose a unique problem for astronomers. Unlike other cosmic phenomena that can be predicted or observed in progression, GRBs are transient. They last from milliseconds to a few minutes and then vanish. Only their afterglow, a fading trace across the electromagnetic spectrum, lingers. Capturing these events requires both precision and luck, as well as an array of instruments scanning the sky around the clock. In recent decades, missions like NASA's Swift and Fermi observatories have significantly advanced our understanding of GRBs. These satellites detect bursts in real time, allowing follow-up observations across various wavelengths. From this, astronomers have learned that not all GRBs are created equal. Some are short, likely caused by the collision of neutron stars. Others are long, linked to the death of massive stars. Each burst is a window into extreme physics, of matter under crushing gravity, of light moving through collapsing space. There is beauty in the violence of a gamma-ray burst, not in its destruction, but in its revelation. These flashes illuminate not just the universe's dangers, but also its history. They tell us where stars lived and died, where elements were forged in fire, and where space itself was reshaped by unimaginable force. And though they remind us of how fragile our existence is, they also affirm that we are here, aware, and able to understand. So the question lingers. In a cosmos stitched with light from 1,000 dying stars, what other silent messengers might already be on their way? What other energies, formed in the heart of collapse, might be crossing the black ocean between galaxies, aimed unknowingly at our pale blue home? From gamma-ray bursts to the swirling debris of ancient collisions, the cosmos holds many hidden dangers, and not all of them come from the collapse of stars. Some come from solid rock, from asteroids born in the early chaos of our solar system, still wandering the dark with silent momentum. These too carry stories of extinction, of impact, of sudden endings. Not all cosmic dangers come wrapped in radiation and born from collapsing stars. Some threats are ancient, heavy, and far more familiar. They come not as light, but as stone, silent wanderers from the birth of the solar system. These are asteroids, remnants of planetary construction, drifting between worlds with quiet momentum and hidden power. Most asteroids never threaten Earth. They circle the Sun in stable belts, particularly between Mars and Jupiter. But some, dislodged by gravitational tugs or ancient collisions, find their paths crossing ours. When they do, even a small one can carry consequences far beyond its size. The Tunguska event of 1908 was one such moment. Deep in the Siberian wilderness, at around 7:15 in the morning, something exploded in the sky. The shockwave flattened more than 80 million trees across 800 square miles, an area larger than some countries. Yet no crater was found. Scientists now believe it was a stony asteroid, roughly the size of a football field. that entered Earth's atmosphere at over 30,000 miles per hour. It disintegrated mid-air, releasing the energy of 15 megatons of TNT. If it had arrived just hours later, it might have struck a major European city. The result could have been the deadliest single event in modern history. But Tunguska was not the first cosmic impact to shape life on Earth, nor the most devastating. 65 million years ago, a much larger object, an asteroid nearly 10 kilometers across, struck what is now the Yucatan Peninsula in Mexico. The impact carved out a crater over 100 miles wide and unleashed a chain of events that extinguished the dinosaurs. Firestorms, global darkness, acid rain, and a collapsed food chain followed. But in that void, mammals found opportunity. Life, though diminished, adapted. And from that adaptation, much later came us. Destruction begets creation, but such outcomes depend on scale, timing, and chance. In today's world, even a much smaller asteroid could devastate a region, a nation, or perhaps trigger global consequences if it struck the wrong place. That's why astronomers around the world have turned their attention to what are called near-Earth objects, or NEOs, asteroids and comets whose orbits bring them close to our planet. NASA's Planetary Defense Coordination Office has been tracking these NEOs for decades. As of today, more than 90% of the largest ones, those a kilometer or more across, have been catalogued. But thousands of smaller bodies remain untracked, any of which could still pose a threat. Their trajectories are plotted, their sizes estimated, their compositions studied. Algorithms forecast their paths years into the future, watching for signs of eventual intersection with Earth's orbit. One name stands out: Apophis. Discovered in 2004, this 370-meter asteroid quickly became the focus of concern. Initial calculations suggested it had a small but real chance of impacting Earth in 2029, an event that would release the energy of hundreds of nuclear bombs. That probability has since been revised downward, and scientists now believe it will miss us. But it will pass within 20,000 miles of Earth, closer than many satellites. So close, in fact, that it will be visible to the naked eye in some parts of the world. Should it pass through a narrow gravitational keyhole during that flyby, its orbit could shift just enough to set up a potential collision in 2036. Though unlikely, the risk remains, and with it, the recognition that early action is our best defense. Unlike gamma-ray bursts, we can see asteroids coming. And unlike supernovae or black holes, we can do something about them. The concept of planetary defense is no longer the realm of science fiction. Strategies now include kinetic impactors, spacecraft designed to slam into an asteroid and change its course ever so slightly. Even a nudge of a few centimeters per second, applied years in advance, can alter an asteroid's path enough to miss Earth entirely. The recent DART mission, NASA's Double Asteroid Redirection Test, demonstrated this principle. In 2022, the spacecraft deliberately impacted Dimorphos, a small moon of the asteroid Didymos. The impact successfully changed its orbit. It was a test, a proof of concept, and a quiet triumph of preparation. International cooperation is critical. No asteroid recognizes borders, and no nation is immune. Programs around the world, in the US, Europe, Japan, and elsewhere, are sharing data, coordinating missions, and planning for contingencies. The United Nations has even begun discussing legal frameworks for asteroid deflection, recognizing that such action may one day be necessary. Still, the question lingers. How do we find peace knowing such threats orbit silently above us, reminders of a chaotic cosmic past that never truly ended? Perhaps the answer lies in awareness, in vigilance, and in the remarkable fact that, for the first time in Earth's history, one species is watching the skies not in fear, but with understanding. There is irony in it. The same asteroid impact that wiped out the dinosaurs cleared the path for mammals. The same cosmos that threatens us has shaped us. And now, for the first time, we have the tools to anticipate, to prepare, and perhaps to prevent. As we continue this journey through cosmic threats, we turn our gaze from rocky wanderers to the heart of our own solar system, to the star that sustains all life on Earth, and yet, in moments of violent flare, reminds us of its raw and unpredictable power. The sun, giver of light, is also a source of solar storms and coronal mass ejections, eruptions that could one day test our world in entirely different ways. At the center of our solar system blazes a star so familiar that we rarely think of it as dangerous. The sun, constant golden warming, has shone upon Earth for over 4 billion years. It feeds our ecosystems, regulates our climate, and marks the passage of days and seasons. Yet beneath its steady glow lies a restless engine, capable of violent outbursts that can ripple across the solar system and threaten the very technologies we depend upon. Solar flares and coronal mass ejections, or CMEs, are two of the most powerful expressions of this inner turbulence. Both originate in the sun's magnetic field, an invisible force twisted and contorted by the sun's rotation and internal convection. When the magnetic field becomes too tangled, it can snap and realign, releasing energy in the form of flares and launching vast clouds of plasma into space. These events, though born in silence, can echo across the void and reach Earth with astonishing effects. The most famous such incident happened over 160 years ago. On the morning of September 1st, 1859, British astronomer Richard Carrington was sketching sunspots when he noticed a sudden flash of intense light on the sun's surface, a white light solar flare. Unbeknownst to him, this flare was just the beginning. Hours later, Earth was struck by a powerful coronal mass ejection. The effects were immediate and global. Auroras lit up the night sky as far south as the Caribbean. In the northeastern United States, they were so bright that people could read newspapers at midnight. Telegraph systems across Europe and North America sparked and failed. Some operators were shocked. Others found they could send messages even with their batteries disconnected, powered entirely by the energy in the air. This was the Carrington Event, and it was a warning. If a similar CME were to strike Earth today, the consequences could be far more severe. Our modern civilization is built upon a complex web of electrical infrastructure, communications networks, and satellite systems. A sufficiently strong solar storm could disable GPS, disrupt aviation, damage satellites, and overload power grids, potentially causing widespread blackouts that might take weeks or months to repair. In a world where everything from financial systems to food delivery relies on stable electricity, the impact would be profound. But what exactly is a coronal mass ejection? Picture a billion-ton cloud of charged particles ejected from the sun at speeds exceeding 1,000,000 miles per hour. These particles carry with them an embedded magnetic field. When they reach Earth, they interact with our planet's own magnetic shield. If the orientation of the incoming field opposes Earth's, it can partially cancel our protective barrier and allow solar energy to pour in, creating geomagnetic storms. These storms are not just beautiful, they can be destructive. Fortunately, we are not unprepared. NASA, the European Space Agency, and other organizations have developed missions specifically designed to study and predict solar behavior. The Parker Solar Probe, launched in 2018, is flying closer to the Sun than any spacecraft before it. It is sampling solar particles directly and measuring the Sun's magnetic field in unprecedented detail. Meanwhile, the ESA's solar orbiter is capturing high-resolution images of the Sun's surface and poles, helping us understand how magnetic fields evolve and erupt. These missions are more than scientific curiosity. They are vital tools in the emerging field of space weather forecasting. Much like we track hurricanes or monitor seismic activity, scientists now work to predict solar storms, identifying sunspots, tracking CMEs, and issuing alerts when Earth lies in the path of an incoming solar wind. With enough notice, satellites can be put into safe mode, astronauts sheltered, and power grids adjusted to minimize risk. Yet even with this foresight, the question remains: what would a modern Carrington event mean for our interconnected world? Could we respond in time? Could we prevent cascading failures across the systems we so often take for granted? Perhaps more than any other cosmic threat, solar storms remind us of the dual nature of the forces that sustain us. The Sun is both nurturer and potential disruptor. It is the source of life on Earth. And yet, like all stars, it is not entirely stable. That we orbit such a star and thrive despite its temper speaks to both the fragility and the resilience of life. We are vulnerable, yes, but we are also watchful. From the surface of our star to the death of distant ones, stellar forces shape the universe in ways both visible and hidden. As we continue our journey, we step beyond our solar system to examine explosions even greater than solar flares, the final acts of massive stars. Supernovae, cosmic events that light up galaxies, forge the elements of life, and yet carry with them the seeds of extinction. The next chapter begins with that violent, luminous end, and the quiet truths it reveals. Among the many phenomena that mark the life and death of stars, few are as dramatic or as important as a supernova. These are not gentle endings. They are violent, magnificent, and rare. In a moment no longer than a heartbeat, a single star's collapse can unleash more energy than our entire sun will emit over its 10 billion year lifetime. That light, that energy, can outshine an entire galaxy, and in doing so, shape the future of everything that follows. Supernovae are the explosive deaths of massive stars, those many times larger than our sun. When such a star runs out of nuclear fuel, its core can no longer support the weight of its outer layers. Gravity wins. The core collapses into an ultra-dense state, often becoming a neutron star, or if the mass is sufficient, a black hole. The outer layers rebound violently off the collapsed core, triggering an outward explosion that tears the star apart. This is the supernova. But the story does not end with destruction. In that chaos, something remarkable occurs. The extreme temperatures and pressures inside the explosion forge elements heavier than iron, gold, uranium, iodine, and many others essential to complex chemistry and ultimately to life. These elements are flung into space, seeding the interstellar medium with the raw materials for future stars, planets, and living organisms. Without supernovae, the universe would be a place of hydrogen and helium. Beautiful, perhaps, but lifeless. Every atom of calcium in your bones, of iron in your blood, of oxygen in your lungs, all of it was born in the heart of a dying star. Creation through destruction. The end of one life gives rise to countless others. Yet as with gamma-ray bursts, supernovae also carry a threat. A sufficiently close supernova, say within 50 light-years, could bathe Earth in high-energy radiation. This radiation could deplete the ozone layer, disrupt the biosphere, and cause widespread extinction. Some scientists speculate that past extinction events on Earth may have been triggered by such cosmic explosions, though the evidence remains circumstantial. Thankfully, nearby supernovae are rare. The Milky Way produces perhaps 2 or 3 supernovae per century, and most occur in the spiral arms far from our solar system. The last observed supernova in our galaxy visible to the naked eye happened in 1604, recorded by Johannes Kepler. A more recent example, supernova 1987A, was observed in a neighboring galaxy, the Large Magellanic Cloud, and became one of the most studied stellar explosions in history. That event gave scientists invaluable data. Neutrinos from the supernova were detected on Earth just before the light arrived, confirming long-standing theories about stellar collapse. Astronomers tracked the expanding shockwave, the light curve, and the remnant cloud over years and decades. It was a window into the physics of matter at its most extreme, and into our cosmic origins. Could the same forces that forged our world one day threaten it? It is not only possible, it is part of the balance. The universe offers no guarantees of permanence. Stars are born, they live, they die, and in their death, they shape what comes next. Our solar system itself may have formed in the wake of a nearby supernova, its shockwave compressing a cloud of gas and dust that would one day become our sun and planets. This is the paradox at the heart of cosmic evolution. That which destroys is also that which creates. The universe is not kind, nor is it cruel. It simply is. Through pressure and fire and silence, it unfolds. The remnants of a supernova often become something even more mysterious. A neutron star, a city-sized sphere with the mass of a sun spinning hundreds of times per second. Or a black hole, a singularity from which nothing, not even light, can escape. These are not mere remnants. They are chapters in a longer story. As we follow that story, we move now to black holes themselves, invisible giants born of collapse, keepers of gravity, of secrets, and perhaps of time itself. In the silent depths of space, where light cannot reach and time itself seems to distort, lie some of the most mysterious entities in the universe. Black holes. They are not stars, not planets, not objects in the usual sense. They are regions, boundaries where the known laws of physics collapse, where matter is compressed into a point of infinite density, and where gravity reigns supreme. A black hole forms when a massive star exhausts its fuel and its core collapses under the weight of its own gravity. If nothing halts this collapse, not even the degeneracy pressure that holds up neutron stars, the result is a singularity, a point of zero volume and infinite mass, wrapped in a boundary called the event horizon. Nothing, not even light, can escape once it crosses that invisible line, hence the name. But not all black holes are the same. Some are just a few times more massive than our sun, scattered across the galaxy as remnants of stellar death. Others, called supermassive black holes, dwell at the centers of galaxies. These behemoths, millions to billions of times the sun's mass, anchor the structure of entire galactic systems. Our own Milky Way harbors such a giant, Sagittarius, a star A supermassive black hole, roughly 4 million times the mass of the Sun, lies 25,000 light years from Earth in the galaxy's core. It is quiet, stable, and far too distant to pose any threat. Despite their reputation, black holes do not roam the cosmos sucking in planets and stars like cosmic vacuum cleaners. Their gravity behaves just like any other mass. If our Sun were replaced by a black hole of equal mass, hypothetically, Earth would continue orbiting as usual, though in cold darkness. What makes black holes strange is not their pull, but the point at which that pull becomes absolute. When black holes do consume matter, the process can be spectacular. As gas and dust spiral inward, they form an accretion disk, a whirling storm of material heated to extreme temperatures by friction and gravity. In some cases, this process becomes so energetic that it creates a quasar, a beacon of light so bright it can outshine an entire galaxy visible across billions of light years. Quasars are powered by feeding black holes, and they offer a glimpse into the early universe when galaxies were young and violent. We have even begun to see black holes directly, not with visible light, but through the shadows they cast. In 2019, the Event Horizon Telescope released the first image of a black hole's silhouette, a glowing ring surrounding a dark center captured from a galaxy 55 million light-years away. It was not just a technical feat, but a conceptual one. Proof that we can observe the edge of the unobservable. Still, many questions remain. What lies beyond the event horizon? Does information truly vanish in a black hole, or is it somehow preserved? Do black holes evaporate over time, as Stephen Hawking proposed, through the emission of quantum radiation? And if so, what happens when they finally vanish? These are not just speculative curiosities. They are central to understanding the nature of time, entropy, and the universe itself. What secrets do these invisible giants hold about the universe's past, and perhaps its future? They are more than objects. They are phenomena that test the limits of human knowledge. Studying them is not just an act of astronomy, but of philosophy. Black holes blur the line between the tangible and the theoretical, between physics and metaphysics. Yet for all their mystery, black holes also serve a structural role. Their gravitational pull helps shape galaxies, stabilize stellar orbits, and anchor clusters. Without them, the cosmic architecture might look very different. Far from being only destructive, black holes may be essential to the universe's long-term evolution. They are silent, unseen architects, reminders that not all forces reveal themselves in light. And yet, even black holes exist within a larger framework. Something else holds galaxies together, something invisible, undetectable by direct means, and yet undeniably present. It does not emit or absorb light, and it does not collapse into stars or planets. But without it, galaxies would fly apart. This is dark matter, the unseen web of the universe. The next chapter in our journey turns to this elusive substance and the gravity it exerts without ever showing its face. For everything we see in the universe, every star, every planet, every glowing cloud of gas, there's something else we do not see. Something vast, silent, and invisible. It does not shine, it does not burn, it does not interact with light in any familiar way. And yet, it is everywhere, holding galaxies together, weaving clusters into filaments, and shaping the very structure of the cosmos. This is dark matter. Though invisible, dark matter reveals itself through gravity. Its presence bends light from distant galaxies, distorts their shapes, and binds them more tightly than visible mass alone could account for. Without it, stars at the edges of galaxies would drift away. Clusters would unravel. The universe would look nothing like it does. The idea of dark matter dates back nearly a century. In the 1930s, Swiss astrophysicist Fritz Zwicky studied the Coma Cluster, a collection of galaxies bound together in space. He noticed something strange. The galaxies were moving far too fast to be held by the visible mass alone. There had to be more. Some hidden mass generating additional gravity. Zwicky called it dunkle Materie, or dark matter. His idea was dismissed for decades, but in the 1970s, astronomer Vera Rubin measured the rotation curves of spiral galaxies and found a similar puzzle. Stars at the outer edges were orbiting just as fast as those closer in, defying expectations. Something unseen was providing extra gravitational pull. And it wasn't just a few galaxies, it was all of them. Today, the evidence for dark matter is overwhelming. Observations of gravitational lensing, where massive objects bend and distort the light of more distant sources, confirm its presence. When the Hubble Space Telescope captured the distorted arcs of background galaxies, it was looking through the invisible fingerprints of dark matter in galaxy clusters, in the cosmic microwave background, in simulations of large-scale structure. The signs are everywhere. And yet, we still don't know what dark matter is. It does not emit, absorb, or reflect light. It doesn't collide with regular matter in any measurable way. It passes through us, through the Earth, through the walls, without a trace. It makes up about 27% of the universe's total mass energy content, 6 times more abundant than ordinary matter. And it has never been detected directly? What could it be? Theories range from weakly interacting massive particles, or WIMPs, to axions, to entirely new forms of physics. Underground detectors, buried in deep mines, search for fleeting collisions. Particle accelerators hunt for signs of unknown particles. Astronomers map its gravitational pull with ever greater precision. But for now, dark matter remains a ghost, inferred but not seen. How does an invisible force shape the universe we see? It is a reminder that our knowledge, vast as it may seem, still glides atop a sea of mystery. The galaxies we observe, the stars we name, the light we follow, all are embedded in a greater framework we cannot touch. The cosmic web, a vast network of filaments stretching across the universe, is composed not just of galaxies, but of dark matter binding them together. These filaments form a scaffold upon which cosmic structures emerge. Voids lie between them, dark spaces where almost nothing resides. And across billions of light years, the pattern repeats. It is order from the unseen. To know that so much of the universe is invisible is not a cause for despair. It is an invitation to explore, to question, to marvel at what remains hidden. We are creatures of light, but we are surrounded by shadow. And in that shadow lies truth. But dark matter is only half the puzzle. If it binds, something else must push apart. If one force holds galaxies together, another drives them away from one another. That other force, even more mysterious, even more dominant, is dark energy. It fills space itself, drives the expansion of the universe, and defies our understanding of gravity. For much of the 20th century, scientists believed that the universe, though expanding, might eventually slow down. Perhaps gravity would halt the outward motion of galaxies. perhaps everything would contract again in a grand reversal. But then, in the late 1990s, observations of distant supernovae revealed something unexpected. The expansion of the universe wasn't slowing, it was accelerating. That acceleration implied the presence of a new force, something counteracting gravity, something embedded in the fabric of space itself. We call it dark energy, and today it is believed to make up nearly 70% of the universe's total energy content, not just invisible, but everywhere. Dark energy is not a substance we can see or touch. It does not clump into galaxies or radiate in waves. Instead, it appears to act uniformly throughout space, stretching it apart at an ever-increasing rate. As space expands, more dark energy seems to emerge, further fueling the process. It is a cosmic feedback loop, silent, continuous, unstoppable. This acceleration changes the fate of the cosmos. In time, galaxies will recede from one another faster than light can travel. Their light will no longer reach us. The sky will grow empty, the stars distant, the universe increasingly cold and dark. Some theories suggest a big freeze, where the universe cools into entropy. Others propose a great rip, where even atoms are eventually torn apart by the expansion of space. We live in a special moment, a moment when the universe is still visible, when galaxies still share their light, when cosmic history can still be read in the stars. But this window will not last forever. The universe is drifting apart, and one day, much of it may lie beyond our reach. Ongoing missions seek to understand this mysterious force. The European Space Agency's Euclid mission, launched to map the geometry of the dark universe, is studying the distribution of galaxies and dark matter over time. By analyzing how structures evolve and how light bends across billions of years, scientists hope to trace the influence of dark energy. Perhaps it is a property of space. Perhaps it reflects something deeper, a flaw or feature in our understanding of gravity. But as of now, we do not know. We see the effect, not the cause. We feel the drift, but not the current. What does it mean for our universe to drift apart, forever out of reach? It is a question not just of physics, but of perspective. We are used to thinking of space as vast but connected. Dark energy rewrites that assumption. It suggests a cosmos that is not only expanding, but accelerating into solitude. And yet, there is beauty in that impermanence. The stars shine now. The galaxies still speak. We are alive during the epoch of light, able to see the universe not just as it is, but as it was. We are witnesses to motion, to change, to the breath of the cosmos itself. The knowledge that it may not always be so, that the night sky will one day fade, does not diminish its wonder. It enhances it. For just as flowers are cherished because they bloom briefly, so too is our cosmic vantage point a rare and precious thing. But even in this expanding universe, galaxies still interact, gravity still pulls, collisions still occur. In the next chapter, we turn to one of the most dramatic and beautiful processes in the universe, galactic collisions, where whole galaxies merge, twist and reshape one another, where chaos births new stars, and where, billions of years from now, the Milky Way will meet its neighbor Andromeda and change forever. Across the quiet darkness of the cosmos, galaxies are not still. Though separated by vast distances, they move, drawn by gravity into slow, majestic encounters. Over millions of years, they merge, stretch, twist, and reshape one another. These are galactic collisions, immense, beautiful, and inevitable. One such collision awaits us In about 5 to 6 billion years, our Milky Way galaxy will meet its neighbor, Andromeda. Today, Andromeda is 2.5 million light-years away, but it is moving toward us at over 100 kilometers per second. The two galaxies are on a collision course, and when they meet, they will not simply pass through each other. They will merge, forming a new galaxy, perhaps elliptically shaped, known as Milkomeda. This merger will not be an explosion. It will unfold slowly over hundreds of millions of years. The vast majority of stars, including perhaps our Sun, will not collide. The space between stars is simply too great, but their orbits will change. Gravitational interactions will fling some stars far from the galactic center. Others will spiral inward, drawn to the core of the merging system. Gas clouds will crash into one another, compressing and igniting new generations of stars in brilliant bursts of light. The result will be a transformed night sky. Our descendants, if they exist, may look upward to see a swirling canvas of stars, stretched into arcs and spirals, glowing brighter than anything seen before. It will be a sky reshaped by time and gravity, a cosmic dance that began billions of years earlier. What might it mean for our descendants to witness such a moment? A sky alive with motion, with the birth of new suns, and the echo of ancient structure collapsing into something new? The fate of Earth itself in this process is uncertain. By the time the collision occurs, our Sun will be nearing the end of its life. Its outer layers may already be expanding, transforming it into a red giant. Earth may have become uninhabitable or even consumed. But if our world, or its distant progeny, still orbits, it could be flung into deep space or drawn closer to the dense center of Milkomeda. Some simulations suggest stable orbits will survive. Others hint at dramatic changes. The Hubble Space Telescope has given us glimpses of such collisions elsewhere. The Whirlpool Galaxy, for instance, shows sweeping arms sculpted by interactions with a companion. Other galactic pairs, the antennae, the mice, the taffy galaxies, reveal long tails of stars, twisted bridges of gas, and glowing knots of newborn clusters. These are not static systems. They are evolving, dynamic, full of drama and creation. In watching them, we glimpse our own future. Galactic collisions are not rare on cosmic timescales. They are part of how galaxies grow and evolve. Every galaxy we see today has been shaped by countless mergers and close encounters. They build structure, ignite star formation, and feed the central black holes that anchor galactic cores. What may seem destructive is, in truth, a process of renewal. The future Milkomeda will likely contain a massive central black hole formed by the merger of the Milky Way's Sagittarius A star and Andromeda's own supermassive core. Surrounding it will be stars old and new, some born of the collision's heat, others preserved from before. It will be a galaxy with memory and transformation. And though the stars will move, though the shapes will change, the fundamental laws of nature will remain. Gravity, motion, light, all will play the roles. The universe does not pause. It dances. To contemplate such a future is to feel both small and connected. Our lives are brief, but the processes that shape the cosmos are continuous. We are part of that story, observers of the present, inheritors of the past, and stewards of memory. Yet even in the grandeur of merging galaxies, we find echoes of another theme, that of creation and destruction. Forces that build also break apart. What is born will one day end, and from that end, something new arises. This theme continues beyond stars and galaxies, reaching even to the rocky surfaces of distant worlds. Across the solar system, far beyond Earth's familiar geology, volcanoes continue to shape worlds. They erupt not just with molten rock, but with sulfur, ice, and gas. On alien moons and scorched planets, these eruptions speak of heat, of pressure, and of stories unfolding beneath the surface. Volcanism, the process of eruption and renewal, is not confined to Earth. It is a planetary language, one spoken across space and time. Take Io, one of Jupiter's moons. From a distance, it appears yellow and blotched, almost diseased. But this strange coloration is the result of constant volcanic activity. Io is the most volcanically active body in the solar system. Its surface is dotted with hundreds of active volcanoes, some of which spew fountains of sulfur and molten rock hundreds of kilometers into space. These eruptions are not driven by internal heat alone. Io's orbit is stretched and squeezed by the gravitational tug-of-war between Jupiter and its other large moons, Europa, Ganymede, and Callisto. This tidal flexing generates heat through friction, melting Io's interior and fueling its explosive surface. Voyager 1 first revealed Io's volcanism in 1979, capturing images of giant plumes rising above the moon's limb. It was a discovery that stunned scientists. Until then, active volcanism beyond Earth had been theory. Suddenly, it was a visible, dramatic fact. Venus tells a different story. Shrouded in thick clouds of carbon dioxide and sulfuric acid, Venus once may have been more Earth-like. But a runaway greenhouse effect transformed it into a furnace. Surface temperatures exceed 460 degrees Celsius, hot enough to melt lead. Volcanoes still dot its landscape, broad, shield-like formations built from ancient lava flows. The Magellan spacecraft, using radar to see through the clouds, mapped thousands of them, and recent data suggest some may still be active today. Unlike Earth, Venus lacks tectonic plates. Its crust is static, like a sealed pressure cooker. Heat builds below the Biao surface, and when it escapes, it does so in planet-wide eruptions. Some scientists believe that a global volcanic resurfacing event occurred 500 million years ago, erasing much of Venus's geologic history and sterilizing the planet's surface. Here, volcanism was not life-giving, it was life-denying. Mars offers yet another perspective. Its greatest volcano, Olympus Mons, is the tallest in the solar system. 3 times the height of Mount Everest, it stands as a monument to slow, steady eruption over millions of years. Mars's lower gravity and lack of plate tectonics allowed lava to pile up without interruption. Though likely dormant today, Olympus Mons hints at a time when Mars was warmer, wetter, and geologically active. These volcanoes on Io, Venus, and Mars illustrate the dual nature of volcanic power. It creates and destroys. It reshapes surfaces, alters climates, and in some cases may provide the heat and chemical energy needed for life. On Earth, life may have originated near hydrothermal vents, volcanic fissures on the ocean floor where heat and minerals combine in rich chemical soups. Could similar processes occur elsewhere? Could volcanoes on alien worlds cradle life as they once did here? That question drives exploration. We look for heat beneath the ice of Europa. We listen for tremors on Mars. We search for gas signatures above Venus's clouds. Each observation brings us closer to understanding not just how volcanoes work, but what they mean. Volcanism is a universal process, a bridge between the deep interior and the exposed surface. It carries the message of a planet's interior out into the open, and in that message we find clues about habitability, about history, and about transformation. Creation through destruction. It is a theme that echoes through every part of the universe, from the collapse of stars to the rise of continents. Volcanoes remind us that even in violence, there can be renewal. And this theme continues beneath the surfaces of icy moons. Moons like Europa, Enceladus, and Titan may harbor subsurface oceans warmed by internal heat. There, in the dark and the deep, life may still find a foothold. In the next chapter, we turn to these icy worlds to explore the hidden seas where geology and biology may yet meet. Beneath the frozen crusts of distant moons, hidden from sunlight and silent to the human eye, lie oceans. Liquid water warmed not by starlight, but by the tug and pull of gravity, by the rhythmic kneading of tidal forces deep within the core. In these alien seas, isolated for billions of years, may exist the ingredients of life, not as we know it, but as the universe might allow. Europa, one of Jupiter's largest moons, is a world of ice and mystery. Its surface is etched with cracks and ridges, like fractured glass or polar sea ice on Earth. These features suggest a soft, mobile layer beneath. A global ocean, perhaps 100 kilometers deep, buried beneath tens of kilometers of frozen shell. That ocean is kept warm by tidal flexing. As Europa orbits Jupiter, the planet's immense gravity stretches and compresses the moon's interior. That motion generates heat, enough to keep water liquid beneath the surface. Enceladus, a smaller moon of Saturn, tells a similar story. In 2005, NASA's Cassini spacecraft flew past Enceladus and made a startling discovery. Geysers, plumes of water vapor, ice particles, and organic compounds jetting from cracks near its south pole, the so-called tiger stripes. These jets are not mere curiosities. They are direct evidence of a subsurface ocean venting into space. Some of that material even escapes Enceladus's gravity, contributing to Saturn's E-ring. Cassini flew through those plumes, sampling their contents. It found water, salts, and simple organic molecules, signs of a potentially habitable environment. Here, beneath an icy crust, warmed by tidal energy, lies a sea of possibilities. Titan, Saturn's largest moon, offers yet another version of strangeness. Its surface is dotted with lakes and rivers, not of water, but of liquid methane and ethane. Beneath that exotic surface, scientists believe there may be a water ocean as well. Titan is cold, distant, and chemically rich. Its thick atmosphere, denser than Earth's, shields it from radiation, and its complex organic chemistry makes it a compelling target for the search for life. Could life exist in these hidden oceans? Could warmth, water, and chemistry combine to form biology? If life emerged near volcanic vents in Earth's deep oceans, why not in the dark seas of Europa or Enceladus? The Europa Clipper mission, set to launch soon, aims to answer these questions. It will orbit Jupiter and conduct dozens of close flybys of Europa, mapping its surface in high resolution, analyzing its ice, and searching for signs of recent or ongoing activity. Its instruments will look for plumes, for magnetic evidence of an ocean, and for the chemical ingredients of life. Meanwhile, new missions are planned for Enceladus and Titan. NASA's Dragonfly, a rotorcraft lander, will one day explore Titan's surface, sampling its chemistry directly. With each mission, we reach farther, ask more refined questions, and listen more closely for the faint signatures of life beyond Earth. What might we find beneath these icy shells, waiting in the dark? Not complex organisms or civilizations, perhaps, but microbes, simple cells, chemical gradients harnessed by rudimentary metabolisms. the first glimmers of life, ancient, tenacious, and alien. To imagine life thriving where sunlight never reaches is to reconsider the boundaries of habitability. It is to see biology not as a rare accident, but as a response to energy and chemistry, wherever they exist. These hidden oceans expand the search for life from planets to moons, from sunlight to tidal heat, from surface to subsurface. They broaden our perspective, not just on where life might be, but on what it truly needs. And as we look down into these dark waters, we also look back to the universe's first moment. For to understand how life arises, we must understand where everything began. Everything we see, every star, every galaxy, every atom in our bodies began in a moment. Not an explosion, but an expansion. A moment of unimaginable heat and density from which space, time, matter, and energy began to unfold. This was the Big Bang, and it occurred approximately 13.7 billion years ago. At that moment, the universe was not a place, but a state, a singularity. There was no outside, no edge, no before, as time itself began in that instant. In the tiniest fraction of a second, the universe underwent a burst of exponential inflation. Space itself expanded faster than the speed of light, smoothing out irregularities and laying the foundation for everything to come. As expansion slowed, the universe cooled. The earliest moments were a sea of fundamental particles, quarks, gluons, leptons, colliding and annihilating in a dense, radiant plasma. Within microseconds, quarks bound together to form protons and neutrons. Within minutes, these fused into light nuclei, hydrogen, helium, traces of lithium. But it would take hundreds of thousands of years for the universe to cool enough for electrons to join these nuclei and form neutral atoms. That moment, the recombination era, allowed light to travel freely for the first time. That light, stretched by billions of years of expansion, now fills the universe as the cosmic microwave background. Discovered in 1965 by Arno Penzias and Robert Wilson, it is a snapshot of the infant cosmos, uniform yet slightly rippled. Those ripples seeded the structure of galaxies and the clusters. After recombination, the universe entered a dark age. For hundreds of millions of years, there were no stars, only cold hydrogen gas. But gravity never rests. Slowly, it pulled matter into denser regions, forming the first stars and galaxies. These early stars were massive, short-lived, and bright. They lit up the universe and ionized the surrounding gas, making the cosmos transparent once more. Galaxies formed from these clusters of stars, merging and growing through cosmic time. Supermassive black holes emerged at their centers. Elements forged in stars, carbon, oxygen, iron, seeded future generations of stars and eventually planets. The simple became complex. The cold became warm. The dark became light. The evidence for this grand story comes from many sources. The cosmic microwave background is our oldest observable signal. Its uniformity and structure match predictions of the Big Bang model. Hubble's deep field images reveal galaxies at various stages of evolution, some billions of light years away, and thus billions of years in the past. These snapshots show a universe in motion, in transformation, in growth. We also see it in the expansion itself. Distant galaxies are receding from us, not because they are moving through space, but because space itself is expanding. The further away a galaxy is, the faster it appears to move. This observation, first made by Edwin Hubble in the 1920s, provided direct evidence for a dynamic universe. How did a universe so vast begin as a single fleeting moment? It is a question that stretches our imagination. From near nothingness, complexity arose. From the uniform, the diverse. From simplicity, life. And through all of it, the laws of physics held. The same forces that governed particle interactions in the first second still guide galaxies today. Gravity, electromagnetism, the nuclear forces, they have shaped the path from singularity to stars, from stars to planets, from planets to observers. To reflect on the Big Bang is not just to look back, but to look inward. We are made of the remnants of ancient stars. We are the universe contemplating itself, trying to understand its origin, from chaos to complexity, from fire to form. The journey of the cosmos is not yet complete. And in that journey, a question has always burned. Are we alone? In the next chapter, we turn from stars and galaxies to the question of life. For if the universe has come this far, might it also have created company? After tracing the birth and evolution of the cosmos, from the Big Bang to the rise of galaxies, we arrive at a question both ancient and urgent. Are we alone? The search for extraterrestrial life is no longer the realm of fiction. It is a scientific pursuit grounded in biology, astronomy, and technology. And it begins not in distant galaxies, but in our own solar system. Mars has long been a focus. Dry, cold, and windswept today, it once held flowing water, rivers, lakes, perhaps even oceans. Its surface bears the marks of erosion and ancient floods. Deep underground, water may still flow. Rovers like Curiosity and Perseverance examine the rocks, drill the soil, and analyze the air for signs of past or present microbial life. Not intelligent beings, but simple organisms. Bacteria, archaea, the kind that once dominated Earth. Beyond Mars, we return to the icy moons Europa and Enceladus, with their subsurface oceans, are among the most promising habitats, protected from radiation, rich in chemical gradients, warmed by tidal energy. These oceans might support microbial ecosystems. Missions like Europa Clipper and future landers may one day sample those hidden seas, seeking biosignatures in the dark. But the search expands beyond our solar system. In the 1960s, astronomer Frank Drake proposed a formula, the Drake equation, to estimate the number of intelligent civilizations in the galaxy. It considers factors like the rate of star formation, the fraction of stars with planets, the likelihood of life emerging, and the lifetime of technological societies. With even conservative inputs, the result often suggests thousands or millions of potential civilizations. And yet, we hear nothing. This silence is known as the Fermi paradox. If intelligent life is common, why have we not detected it? Why no signals, no probes, no visitors? There are many possible answers. Perhaps intelligent life is rare. Perhaps civilizations destroy themselves before mastering interstellar travel. Perhaps they do not use radio. Perhaps they choose silence. Or perhaps the distances are simply too vast, the timescales too long, the signals too faint. These are hypotheses, not conclusions. The truth remains unknown, but our tools improve. The search for extraterrestrial intelligence, or SETI, scans the sky for artificial signals, narrow-band radio bursts, repeating patterns, anything that might indicate technology. So far, it has found none. But the search continues, broader and deeper than ever. Meanwhile, missions like Kepler and TESS search for exoplanets, worlds orbiting distant stars. They have found thousands. Many lie in the so-called habitable zone where temperatures could allow liquid water. Some are rocky, Earth-sized, and orbit-stable stars. Future telescopes will analyze their atmospheres for gases like oxygen, methane, and carbon dioxide, signs of possible biological activity. We are perhaps on the cusp of discovery, or perhaps the wait will be long. Are we alone, or is the universe teeming with life we've yet to find? That question drives not just science, but imagination. It shapes our sense of identity. For if we are the only sentient beings, then we are precious and rare. And if we are not, then we are part of something larger, a tapestry of awareness woven through the stars. Either answer is profound. And yet, even in the absence of evidence, the search continues. We explore not because we are certain, but because we are curious, because we ask, because we look. This spirit of inquiry, this resilience and wonder, is the defining trait of our species. From cave paintings to space telescopes, from myths to models, from Earth to the stars, we persist. From the searing blast of gamma-ray bursts to the hidden oceans beneath icy moons, we have journeyed across a universe filled with both peril and possibility. Each chapter in this vast story has revealed a new face of the cosmos, some terrifying, others quietly beautiful, all bound by the same laws of nature. The same stars that die in violent explosions also forge the elements that make life possible. The same space that tears galaxies apart also cradles them in gravitational embrace. We've seen how gamma-ray bursts, though rare, hold the power to strip away atmospheres, how asteroids, in silence, have altered the course of evolution, how the sun, our provider of light, can erupt in storms that challenge our modern world. We've watched galaxies collide, stars explode, and black holes bend the very fabric of space. Yet through all of this, we've also seen humanity's response. We are not merely bystanders to the cosmos. We are students, observers, creators of instruments that stretch our vision, thinkers who build models, engineers who design probes to touch the sun and land on comets. We track near-Earth asteroids, plan strategies for deflection, monitor solar activity, and send messages into the void. We listen, we reach, we learn. Our planet, though small, occupies a rare position, not just in the habitable zone of our sun, but in a relatively calm region of the Milky Way. Away from galactic centers, shielded from the chaos of frequent supernovae. Earth resides in what some call a galactic Goldilocks zone. Not too close, not too far, just right. It is a fragile balance, and a remarkable one. This balance has allowed life not only to emerge but to persist through ice ages, extinctions, and solar flares. It has allowed thought to form, language to evolve, curiosity to flourish. From the spark of flint to the hum of quantum computers, from early sky watchers to deep space telescopes, we have reached outward with questions, and sometimes with answers. The universe is vast, indifferent perhaps, but not unknowable. Each discovery brings us closer to a deeper truth, that we are connected to all of it, by atoms, by gravity, by light. We are stardust, shaped by cosmic time, witnessing the echoes of creation. And in this moment, this brief flicker of awareness in a universe so old, we have the chance to reflect, to marvel, to ask, what comes next? What mysteries remain? What will the next mission find, the next telescope reveal, and the next generation uncover? As we rest beneath the stars, what mysteries await our discovery? Let this journey be a beginning, not an end. There is more to learn, more to explore, more to understand. And each question we ask brings us one step closer to understanding our place in this grand design. If you've enjoyed this journey through cosmic wonders and dangers, consider subscribing to the channel, like the video, Leave a comment sharing what part of the universe fascinates you most. Your curiosity fuels what we do next. In awe, in humility, and in hope, we look to the stars, and the universe continues.